Hi there! So, if you didn't already know, two of your judges, us, Brittany and Selena, are specialists in spherical geometry. So, we just wanted to let you guys know some tips for next competition. Spherical geometry is the geometry of two-dimensional surfaces of a sphere and is defined as the study of figures on the surface of a sphere. Two practical uses of spherical geometry are navigation and astronomy. On the sphere, points are still defined the same, but lines, however, are not in spherical geometry. Lines are not defined as straight, but rather as the shortest path between 2 points. These are referred to as geodesics. A sphere is essentially defined as a closed surface figure, which is 3D. The sphere is formed by a set of points which are all equal distance from the center of the sphere. The radius is known as the distance from the center of the sphere to the sphere's surface. An arbitrary line is a line that does not lie on the sphere. An arbitrary line can either not intersect the sphere at all or intersect the sphere at a point, only if the line is tangent to the sphere at one point of intersection, or it can just intersect the sphere at precisely 2 points. When the arbitrary line passes through the center of the sphere and intersects the sphere at 2 points, the points of intersection from the antipoints of a sphere. An example of this would be the north and south poles. The relationship between spheres and arbitrary lines, and the relationship between spheres and arbitrary straight planes is very similar. When arbitrary straight planes cut through a sphere to form a circle of intersection in three-dimensional space, it can either not intersect or one point of intersection, only when the plane is tangent to the sphere at that point, and instead of both of these. An indefinite number of points of intersection. Great circles are defined as circles that share the same radius and center of the sphere they intersect. Great circles are the largest circles of intersection one can obtain by passing a straight plane through a sphere. An example of this would be on the globe. The equator forms a great circle. Small circles are circles that's radii measure less than the sphere they are on the radius. One of the main reasons that navigation of one of the main uses of spherical geometry is because navigators often use great circles to figure out the most efficient routes to their destination. A spherical triangle is known as the result of three great circles intersecting on a sphere and their enclosed area.
The angles between two great circles are measured by calculating the angle between the planes on which the two great circles themselves lie. This is possible because of the fact that the spherical triangle formed by two intersecting arcs of great circles is equal to the angle between the tangent lines formed when the great circle's planes touch the circle at their common point. In a sphere, it is also possible for there to be triangles with sums of angles greater than 180 degrees. In this example, the two meridians of the longitude are separated by an angle of 90 degrees each, and they are both perpendicular to the equator, and so each angle in the spherical triangle is 90 degrees, and that makes the sum of the angles 270 degrees. The reason the sum of the triangle exceeds 180 degrees is because the angles have a natural curvature which makes their measure larger than a straight triangle. In spherical geometry, the sides of a spherical triangle are also measures in degrees, and they equal the measure of the angle opposite to them. So in all of this, the sides equal to 90 degrees because all the angles equal to 90 degrees. Referring back to the previous example of navigation and how it is one of the main uses of geometry. A main application of this is finding the shortest distance around the globe, which is essential for pilots. The way to find this is often done using the solution of spherical triangles. In this, we use the cosine law for triangles on a plane. C squared equals A squared plus B squared minus 2AB cosine C. We can use this formula when we are given two sides of the spherical triangle and measure of the angle between these two sides. The solution for the triangle involves finding the third side of the spherical triangle. The ultimate formula for finding third side distance is cosine A equals cosine B plus sine B times sine C times cosine A. There are no parallel lines in spherical geometry. All great circles and geodesics intersect each other, making it impossible for there to be parallel lines. The closest thing to parallel lines are parallels of latitudes, which are equidistant lines on the sphere.